In the previous class, we discussed the transmission efficiency of a communication system. We know how to calculate the efficiency of transmission of a communication system in decibels. Then we considered a cascaded communication system, and there were 3 blocks in this cascaded communication system. There were 3 elements in this cascaded communication system. Element number 1, element number 2, and element number 3. And we discussed the overall efficiency, the overall transmission efficiency of the cascaded system, and we concluded that the overall transmission efficiency of a cascaded communication system in decibels will be equal to the transmission efficiency of block number 1 in decibels plus the transmission efficiency of block number 2 in decibels plus the transmission efficiency of block number 3 in decibels. Today we are going to discuss the nature of light, the behavior of light. So sometimes light behaves like electromagnetic wave, and sometimes light behaves like particles. So we are going to discuss the electromagnetic wave behavior of the light and the particle nature of the light in this particular class. So let us talk about the electromagnetic behavior of the light. Electromagnetic nature of light. The energy of the light wave behaves like the energy of an electromagnetic wave. So basically, light behaves like an electromagnetic wave. And we know that an electromagnetic wave has 2 fields: the magnetic field intensity, which is represented by capital H, and the electric field intensity, which is represented by capital E. So the electromagnetic wave consists of 2 fields, that is electric field intensity and magnetic field intensity. And if this wave is a transverse electromagnetic wave, in other words, if it is a uniform plane wave, then the electric field intensity will be normal to the magnetic field intensity. These 2 fields will be mutually orthogonal. They will be perpendicular to each other. We know that this electromagnetic wave, this light wave, oscillates with very high frequency. The frequency of the light wave is very, very high. And the light frequency ranges from 1.5 into 10 raised to power 14 hertz to 15 into 10 raised to power 14 hertz. And its free space wavelength ranges from 0.2 micrometer to 2 micrometer. if we consider this wavelength range in nanometer, so we can say that the free space wavelength of the light wave ranges from 200 nanometer to 2000 nanometer. So this is the wavelength range of the light wave. We also know that the frequency of electromagnetic wave is inversely proportional to its wavelength. And we know the graphical relationship between the frequency and the wavelength. If we consider the wavelength along x-axis and frequency along vertical axis, then the graphical relationship between the frequency and the free space wavelength is shown in the diagram of this slide. We know the mathematical relationship between the frequency and the wavelength of an electromagnetic wave. If we look at equation number 1, equation number 1 is valid in free space. The frequency of an electromagnetic wave in free space will be equal to c by lambda, where c in equation number 1 represents the speed of light, and lambda in the denominator of equation number 1 represent the free space wavelength. So this is the mathematical relationship between the frequency and the wavelength of an electromagnetic wave in free space. If the electromagnetic wave travels in any other medium, then equation number 1 is not valid. Then we use equation number 2. So in any other medium, the mathematical relationship between the frequency and the wavelength of an electromagnetic wave is given by equation number 2. The frequency is equal to v by lambda. So if the velocity is known and the wavelength is known, we can calculate the frequency and so on. Whenever light wave travels from one medium to another medium, its frequency is constant. Its frequency will not change, while its velocity and its wavelength will change. So whenever an electromagnetic wave travels from one medium to another medium, the frequency of the electromagnetic wave will be constant and its velocity and wavelength will change. If the velocity increases in the second medium, then the wavelength increases as well. Why? Because frequency is constant. Similarly, if the light wave travels from one medium to another medium and its velocity decreases in the second medium, so if its velocity decreases in the second medium, its wavelength decreases in the second medium as well. So the velocity and the wavelength will change and the frequency will be constant. Its frequency does not change. Well, the maximum velocity of the light wave occurs in free space. That is represented by c. And the numerical value of the speed of light in free space is 3 into 10 raised to power 8 meter per second. This is the maximum possible speed of the light wave they take place in free space. In any other medium, the velocity of the light wave will be less than c. The velocity or the speed of the light wave will be less than 3 into 10 raised to power 8 meter per second. The velocity of the light wave in any other medium is given by this mathematical relationship. You guys can see the mathematical relationship between the velocity of the light wave in any other medium and in the free space. So the velocity of the light wave in any other medium is given by c by n. C is the speed of light in free space, and n is the refractive index of the medium where you guys want to calculate its speed. And n for free space is 1. For any other medium, n will be greater than 1. What is n? N is the refractive index of the medium. So if you guys want to calculate the speed of the light wave in any other medium, you guys can use this mathematical relationship, that is v is equal to c by n. N is the refractive index of the medium. So if the refractive index of the medium is known, you guys can calculate the speed of the light in that particular medium. Now we talk about the electromagnetic spectrum of the light wave. We discuss the electromagnetic spectrum of the light wave. We know that the frequency of the light wave ranges from 1.5 into 10 raised to power 14 hertz to 15 into 10 raised to power 14 hertz. While the free space wavelength of the light wave ranges from 0.2 micrometer to 200 micrometer, from 0.2 micrometer to 2 micrometer. If we discuss this wavelength range in nanometer, we can say that the free space wavelength of the light wave ranges from 200 nanometer to 2000 nanometer. And we can divide the electromagnetic spectrum of the light wave in 3 regions. We can divide the electromagnetic spectrum into 3 regions. The first region is known as ultraviolet region. We will talk about all these 3 regions after some time. So there are 3 regions in the electromagnetic spectrum of light wave: the ultraviolet region, the visible region, and the infrared region. So let us discuss these 3 regions of the electromagnetic spectrum of the light wave. First of all, we discuss the first region of the electromagnetic spectrum of the light wave, that is known as ultraviolet region. The wavelength of the ultraviolet region ranges from 0.2 micrometer to 0.4 micrometer. So in this particular range, the light wave is known as ultraviolet light. In this region, gloss, that is silicon dioxide, attenuates the light wave up to such extent that even small communication links are not possible in this region. So small communication links are not possible in this region as well. There is too much attenuation in this region of the electromagnetic spectrum. we discuss the second region of the electromagnetic spectrum of the light wave, that is known as visible region. In this region, the light is visible. And the wavelength of the visible region of the light wave ranges from 0.4 micrometer to 0.6 micrometer. That is from 400 nanometer to 600 nanometer. And we know that light consists of 7 colors. And the light is visible in this particular region, so there will be 7 colors of the light. 0.4 micrometer represents the blue color, and 0.6 micrometer represents the red color of the light. In this region, glass attenuates the light up to such extent that small communication links are possible in this region. So we can transmit the light with the help of glass through small communication links from one place to another place. So small communication links are possible in this region only. We go ahead to region number 3 of the electromagnetic spectrum of the light wave. In this region, the wavelength changes from 0.6 micrometer to 2 micrometer. If we discuss this wavelength range in nanometer, we say that the wavelength ranges from 600 nanometer to 2000 nanometer. And we use this region for the fiber optic communication system. The fiber optic communication system takes place in this particular region. The wavelength ranges from 0.6 micrometer to 2 micrometer. And there are 3 transmission windows in this region. That is 0.85 micrometer, 1.3 micrometer, and 1.55 micrometer, where the attenuation of the light in the glass is almost negligible. So there is almost negligible losses in this region. This is why we use this region of the electromagnetic spectrum for communication purposes. Fiber optic communication takes place in this region. So the electromagnetic spectrum of the light wave is given in the diagram of this slide. We take the wavelength along the horizontal axis. There is a wavelength along the x-axis of this graph, and there is a frequency along the vertical axis of this graph. And you see the frequency changes from 1.5 into 10 raised to power 14 hertz to 15 into 10 raised to power 14 hertz, and the frequency of the light wave is pretty high. As far as the free space wavelength is concerned, you see that the free space wavelength of this electromagnetic spectrum changes from 0.2 micrometer to 2 micrometer. And you can see the 3 regions of this electromagnetic spectrum. The first region, which is from 0.2 micrometer to 0.4 micrometer, is the ultraviolet region. The second region, which is from 0.4 micrometer to 0.6 micrometer, is the visible region of the electromagnetic spectrum. And then the third region, where the wavelength changes from 0.6 micrometer to 2 micrometer, is the infrared region. And the fiber optic communication takes place in the infrared region of this electromagnetic spectrum. So the scientist believes that the electromagnetic wave behaves, that the light behaves like electromagnetic wave. Now we talk about the second nature of the light wave. Some scientists believe that the light behaves like particles. So let us discuss the particle nature of light. So light consists of tiny particles, and these tiny particles are known as photons. We know that energy of a single photon can be calculated with the help of equation number 1. In equation number 1, WP represents the energy of a single photon, and WP, the energy of the single photon, will be equal to HF. H is the Planck constant and F is the frequency. And the numerical value of the Planck's constant is 6.63 into 10 raised to power minus 34 minus 34. So if we put the value of the frequency in equation number 1, we know that the frequency is equal to C by lambda. So if we put this frequency, the value of this frequency in equation number 1, we get equation number 2. Equation number 2 gives you the energy of a single photon in terms of wavelength. So the energy of a single photon can be calculated with the help of equation number 2. The energy of a single photon in equation number 2 is equal to hc by lambda. C is the speed of light in free space. The numerical value of C is 3 into 10 raised to power 8 meter per second. If there is a beam of light having n number of photons, so if you guys want to calculate the number of photons in a beam of light, we can calculate the total energy of the beam of light with the help of equation number 3. We find out the total energy of a light beam with the help of equation number 3. W on the left hand side gives you the total energy of the light beam, and gives you the number of photons in the light beam, and W of P gives you the energy of a single photon. So we can calculate the total energy of the light wave. We can calculate the total energy of the light beam with the help of equation number 3. If the number of photons in the beam is known, and if the energy of a single photon is known, we can calculate the energy of a single photon. Similarly, if the energy of a single photon is known and the total energy of the beam is known, we can calculate the number of photons, that is n. Now we do example number 1.4. The statement of example number 1.4, example number 1.4 says, find the number of photons incident on a detector in 1 second if the optic wave is 1 microwatt. Find out the number of photons incident on a detector in 1 second if the optic power is 1 microwatt and the wavelength is 0.8 micrometer. So we do the numerical example, and this example is 1.4. So we calculate the total energy of this light first. The total energy will be equal to power multiplied by time. The power is 1 microwatt and the time is 1 second. So if we calculate the total energy with the help of the first equation of this light, the total energy comes out to be 1 into 10 raised to power minus 6 watt second. So 1 into 10 raised to power minus 6 watt second is the total energy of this light beam. Then we calculate the energy of the single photon with the help of this equation, which is hc by lambda. WP is equal to hc by lambda. We put the values on the right hand side of this equation. You see h is 6.63 into 10 raised to power minus 34. C is 3 into 10 raised to power 8. And the free space wavelength is given to you guys in example number 1.4, that is 0.8 micrometer. You see, the free space wavelength is 0.8 micrometer. So in WP, we put the value of H, we put the value of C, and we put the value of lambda. Lambda is 0.8 into 10 raised to power minus 6 in this numerical example. So we find out the energy of the single photon. The energy of the single photon is 2.48 into 10 raised to power minus 19 watt second. Now we use equation number 3 to find out the number of photons. Look at equation number 3 of this slide. We can find out the number of photons with the help of equation number 3. And you see, you guys can find out n from equation number 3. N will be equal to the total energy divided by the energy of a single photon. So we use this equation number 3 to find out the total number of photons. You see, the total energy of the light beam is 1 into 10 raised to power minus 6. And the energy of a single photon is 2.48 into 10 raised to power minus 14. So the total number of photons in this light beam is 4.03 into 10 raised to power 12 photons. So inshallah, we will talk about the advantages of the optical fiber in the upcoming class. Thank you so much. Bye-bye.